Hi, I'm Mike Stanzik and this is Digital Electronics Classroom. Thanks for joining us today. Hope you find this to be a valuable experience. We are talking about Boolean logic now, and logic gates, truth tables, gate diagrams. That's the unit that we're on. And today's lesson, we're going to take a Boolean expression and we're going to build a logic gate from that Boolean expression. All right, let's get started. So we'd say this is Boolean expressions to logic gates. So let's start with the Boolean expression. F1 is xy or y z bar. First question I'm going to ask myself is, how many different variables do I have here? I have x, y, y, z bar. So you can see that the inputs that we have are x, y, and z. And we're going to perform three operations. We have an inversion, we have an and we have an or. So we need the AOI, or, and, or, inverter, framework for us to build this this gate network. Okay, so you can kind of build this any way that you would like to, but we would like to make it readable to our to our users, and so there is sort of a standardized structure in doing this, and so I will talk through it as I build it. So first, we have our three inputs at the top, and then we're going to draw a line that represents a wire down from that point. You know what, I'm going to move this over a little bit so that we don't get into our picture-in-picture. Let's do it right here. So we have our three inputs. Sorry about that little guttural noise of disgust. Okay, enough of that. All right, here we got x, y, and z. So we have x, y, and z. And so these are connections that I can connect to as I build my network, and I'm going to build it over on this side right here. Okay. So this first section we can call the inverter section. And so this is where I will take either my uncomplemented literal or a complemented one. And so I'm going to make an inverter right here, and then also draw a line down for each of these. Now, I'm not trying to simplify this diagram at this point. I'm just kind of showing you a standardized approach. We might not use these inversions, but I'm just putting them out there so that we can have them if we do want them. And so here is our inverter section. Now we're going to go to a second section. And then this second section has to do with our terms. So what type of situation do we have here? We have a sum of product terms. So those are our product terms. And so that's going to come next. So we'll have a product, which is an and. We'll have two AND gates here. So this is the AND section, or we can say the product section. Okay. And what goes into these AND gates? Well, we have X and Y going into one of the AND gates. So I can pull off an X. And now you're going to have to make a dot to show that it's connected, because I'm going to go across a bunch of these lines here, and I don't want them to be connected. So we have X there, and then I have Y right here. X and Y. And for the second gate, I want Y, and I want Z inverted. So this is the case where I'll take it from the inverted line and put it into my my AND gate, just like that. And so this has X and Y coming into this first AND gate. So this is X and this is Y. and then we have y and z bar coming into the second AND gate, just like that. So this is our AND section. So now we'll go to our third section, and this is where we're going to OR the whole thing together. So this is going to OR the whole thing together, and so we need an OR gate, just like that. And this OR gate then is our OR section, our third section, and this is our sum. So I can take my two outputs from my AND gates, and those are the things, these two terms are ORed together. So we have a term coming out of each of these AND gates, and then we'll put it into our OR gate, and that'll be ORed together. So this term is xy, ANDed together, and this term is y, z bar, ANDed together, and then we exit, and we have our function f1. So this gate diagram implements this logic expression, and if we were to build this in, with using real life components, then we can expect that we would get this functionality that's described by this Boolean expression. Excuse me. I do want to reinforce that this is a sum of products configuration, SOP. And so we have our product section right here. So this is the P. And then we have our sum section right here. That's the S. All right, great. Let's do another example. So in the second example, this is a great time for you to start to think about, making predictions about what it's going to look like. And so this is, a little bit of a self-quiz, a little practice for you to try to do it on your own before you see the answer, and then you can get some feedback right away. So we have our second function, f2, and this one, as you might expect, is going to be written in product of sums form, and we got w or x bar. And I also threw in a little surprise for us there. So how many literals do we have this time? How many inputs? Different inputs? X, Y, Z, and there's a W there. So we have 4. So our inputs are W, X, Y, and Z. So let's go ahead and start to build this up. W, X, Y, and Z. And this time, I'm only going to put the inverter in if I need it. And we can see from these expressions that the only one that I need it for is X. And so make a dot to show that there's a connection there. Put my inverter, and there we have our setup. Great. Okay. So let me go ahead and build the other sections. So we have terms here that are OR terms. So in this case, these are going to be ORed. And then we have an AND term that takes care of the whole thing. So I'm going to start with an OR section. Okay, there's my OR section. And then I'm going to have an AND section. And since we have two terms, there's going to be two inputs to this AND gate. And since we have two terms internally for our, each of our terms have two terms, or a literal and a term, a literal and a literal. So those are two input OR gates as well. All right, so here is where I threw you a little bit of a curveball, because this isn't a literal. This is actually another term, and it's an AND term between Y and Z. And so we have a fourth section here, if you will, these intermediate kind of ANDs and ORs that might happen. And so I'm just going to draw an AND gate right here, and that AND gate will feed into our first OR gate, like so. So now I'm going to connect everything. I'm just going to use a blue color here for all these connections. Maybe no, you know what, I'll use black. Okay, great. So what goes into this first OR gate? We have X going in, and then the ANDing, or the product of Y and Z. So let's start with Y and Z. Connect with a dot. Connect with a dot. And then I need an X right here. Oh, you know what? I did the inverter on the wrong variable. Thanks for catching that, guys. My students in my classroom, oops, yeah, I'm pressing the wrong thing. I'm a teacher, and some of my students will, you know, right quick say, Mr. Stanzi, and sometimes they don't, and then I'm like, why didn't you guys tell me that? Because they knew, they just didn't tell me. Sorry about my inefficiency this morning. Had a little coffee. Okay, so we need an X. Boom, X. Exciting. And now we need a W and an X bar. So the W is going to come from all the way over there. Make sure I draw my dot. Try to do a straight line. And then there's my X bar into the end. And hey, woohoo! Exciting, we have our answer, we have F2. Okay, so double check. We got X or Y bar Z, X or YZ, X or Y and Z. Great. Then we have that ANDed with W or X bar. And there we have it. That is a nicely drawn logic diagram, and it's clearly set up with its different sections. So we have our three sections here. We have our inverter, we have our OR section, and we have our AND section. And again, we're using the AOI framework to draw these. Thanks for your time. Thanks for watching. I hope you find this lesson valuable. And you can always email me or leave comments, and then I'll try to get to those or make another video to answer your questions. I'm Mike Stanzik. This is Digital Electronics Classroom. Have a wonderful day.